technology. Luca Biferale is going to be talking to us about Lattice Boltzmann models of complex flow.
Yeah, thank you very much. Thank you first of all to Uwe and Daryl for the invitation to this nice program and to the school here. And I'm going to tell something today about, I prepared a sort of very, let's say, basic pedagogical introductions to Lattice Boltzmann methods. And of course, being a method that is very widely used, for many different applications, I will not be able to really cover all possible applications, so therefore I will spend most of the time to give you the idea about the method, why it is used, what are the pluses and what are the minuses, at least from my point of view. And then I selected a few possible applications, in particular the one that I prefer. And then eventually, for those of you that are interested to other applications, I can point to the right literature. And I also here selected a very personal and biased selection of papers that I think it might be useful for those of you that do not know too much about the method and that might want to enter in the field. There are mainly review papers about Lattice Boltzmann methods. And then I also selected a few review papers or basic important papers that I think they worth to be read by those of you that are interested to contact line dynamics and multi-phase or multi-component flows, at least concerning the kind of applications that I will discuss today. And this is more or less the plan of the lecture. I will start from the simplest case, the one that is more, the one that I would say is rigorously under control. It is how to set up and how to define these Lattice Boltzmann methods for single-phase fluids, so for simple fluids, but which might develop complex dynamics, so might develop complex flow dynamics. And then I will move to other cases that are less under control from a rigorous point of view, even though, we and the people that are used them are confident that they might really be used in a quantitative way. And therefore I will move from single phase to multi-phase, but isothermal, therefore where you might have a liquid and its vapor gas in equilibrium, but you keep the system at the same temperature homogeneously. I will then try to convince you that the method is very useful and potentially useful to describe many interesting physical properties, not only the interface between the gas and the liquid, but also the contact line physics, and therefore what happens when you have the gas and the liquid and a solid wall, and you are able to tune parameters to change the wettability properties of the wall. Then I will enter a few applications really briefly to give you the flavor of how quantitative the methodology can be. And I will speak about this the wetting transition in microcoupled channels. Then I will move to I don't know, maybe I will speak first about that indeed. I will move to multi-component situations, therefore two fluids like oil and water that might again be miscible or immiscible. And again, I will give you a few technical details on how to build up Lattice Boltzmann to describe this kind of physical systems. And again, I will be interested to contact line dynamics, and I will address a very specific problem about coating of a plate, both in the case of when you pull the plate inside a bath or when you withdraw the plate from the bath. And finally, I will add some complication, more complication by describing also a very important point, which is technically hard, that is how to include in a self-consistent way temperature in the game. That is how to really control in a quantitative way the exchange of it whenever you nucleate or you condensate in your system. And if I have time, I will say a few words about the case where you not only have a multi-phase physics, so you not only have the interface that need to be tracked inside your system, but also the fluid is very complicated because you are at high Reynolds number. And therefore, I mean, the paradigmatic example that I would like to discuss, for instance, could be the case of boiling convection, where you have a fluid heated from below, and this fluid is close to its critical temperature, and therefore you may nucleate bubbles in the system, and you may have a convection. And if the temperature jump is high enough, the convection becomes turbulent. You are far from the situation that Edgar was describing before, that is, you are at high Rayleigh number. And there you have, both complexities in your problem. Both the physics is complex because you have a multi-phase system, and the fluid is complex because it is highly chaotic and highly turbulent. So,
sorry, can you turn your microphone on?
Oh, sorry.
Can you press the button once? Press the button on the top once. It will go green. Green.
This one?
Right. Yep.
Okay. Now it's on. Sorry. I will not repeat. So, let's move on. So what is the typical situation that you would like to discuss? I mean, I will mainly speak about a numerical method, one numerical method indeed, in particular. The typical situation you would like to discuss is the following one, right? You have a fluid on one side, a fluid on the other side. It could be liquid and it's vapor. For the moment, it's not so important to discriminate. And eventually, you have a boundary. So you have also a contact line here. And eventually, the boundary is very complicated, may have chemical patterning, so you may have different non-homogeneous wetting properties, or you might have strongly geometrical, complicated walls, like, for instance, some fractal roughness. I mean, you can imagine the situation as the most complex situation you want to describe, and then your goal is to try to make it, to set up a numerical method that is good to simulate in a quantitative way this kind of physics. Well, of course, you can write down the equation of motion. You have the equation of motion for the fluid 1, the equation of motion for the fluid 2. Then you write down the boundary conditions between the two fluids. So you want that the normal velocity of the two fluids is the same. You do not is the same, and it is the velocity of the interface. So you do not want mass across the interface for the moment, at least. You want the tangential velocity is the same because physics does not like discontinuity in the tangential directions. And then you want to impose also the typical boundary condition on the stress. You want the jump of the stress from one side and to the other side is in the normal direction to the interface is proportional to the curvature and to the surface tension, and in the tangential direction is eventually proportional to the derivative of the surface tension if you have the surface tension which is not constant along your interface. And this boundary condition, I mean, it's very easy to realize that in the case where gamma is a constant, so you do not have this term, ends up to the classical and you do not have a velocity inside. I mean, you are in a static situation, and that ends up with the classical Laplace law, where the jump of the stress tensor is just proportional to the jump of the pressure inside and outside the interface, and the curvature is just 2 times r, where r is the local curvature of your interface if you have a spherical droplet. So these are the equations of motion that everybody believes. And we would like to have a numerical tool to simulate this problem. You understand that the problem, from a numerical point of view, the main problem is here, is at the interface. Because in principle, the interface is infinitely thin for almost all of your applications. If you are far from the phase transition, the interface is of the order of of 1 nanometer maximum, a fraction of nanometers most of the time. So on a macroscopic scale, the problem that you would like to solve numerically is a problem where you have an incompressible fluid, let's say here on the left, an incompressible fluid on the right, but that are coupled by a movable boundary condition, and the dynamics of the boundary conditions depends on the fluids on the right and on the left side. And this movable boundary condition should be infinitely thin, should be singular in some sense. I mean, as far as most of the applications are concerned. And this is tough. This is very difficult from a numerical point of view. because you need to solve a Navier-Stokes equation here, Navier-Stokes equation there, and change the boundary condition in a way that is fully coupled in a nonlinear way and in a local way because of the pressure with the two sides of your fluid. As a matter of fact, except for a few simple cases, a few bubbles or a few droplets in an almost quiescent flow, there are not, to my knowledge, good numerical methods that are able to attack the system numerically if the interface is taken infinitely thin, as it should be. The second problem with the interface infinitely thin, and the other problems with the interface infinitely thin are not only on the numerical side, but there are also there are problems also from a conceptual point of view. I mean, of course, whenever you have the interface which is infinitely thin, you might have troubles to describe many important physical phenomena. For instance, thanks to coalescence of two air bubbles. It is, of course, singular at the merging of the two interfaces, or a nucleation of a second phase, the birth of a droplet inside an homogeneous phase. If you think your interface to be infinitely thin, is another singular problem that you cannot solve numerically. The moving boundary condition I already said, and the other problem that has already been discussed in this school, in particular by Len Piesman the first day, is about the fact that if the interface is infinitely thin, and if you are close to a contact line here, and you want to describe the system within the hydrodynamical equation of motion, here you have a viscous singularity at the contact line because the stress the viscous stress becomes infinite as soon as you move. And therefore, you need to go, even if the system is macroscopic, even if these scales are large, you need anyhow to intervene here, close to the contact line, to slightly modify this equation in one way or another, and then we can discuss how, because you want to remove the hydrodynamical singularity that you would have here if you impose no slip boundary condition at the contact line. And so what is the recipes that I would like to sell or to oversell to you today is that one very good way to attack this kind of phenomenology is you need to pay a price. You need to relax something. And the assumption that we relax, that we would like to relax, I mean, not only us, but many people in the community, that we would like to relax is the assumption that the interface is infinitely thin. So we pay the price to have an interface which is thick. How much? 2, 3, 4 grid points. We will go back to that point. Of course, whenever you pay this price, you must be very careful, because if the interface is thick and it is, let's say, 4 grid points, it means that if you really want to match the physical dimension of the system that you are simulating, because the interface in reality is 1 nanometer, it means that if you have 100 grid points in your domain or 1,000 grid points, you are indeed describing a system on a scale of a few nanometers, 10, 20, 100 nanometers, which could be of interest. There are many interesting problems at the scale of 100 nanometers, and where then you would be quantitative both on the effect of the thickness of the interface and on the macroscopic scales in your system. On the other hand, if you want to apply and to study systems that are on a, let's say, everyday scale, 1 meter, of course, if you have 1,000 grid points on a system that is 1 meter large, it means that your grid point is of the order of 1 millimeter. And therefore, you are describing a system where the thickness is a few millimeters. Of course, it does not exist. What is the hope? The hope is that, nevertheless, if the outcomes is such that the thickness of the interface is not important, that is, if the outcomes is such that anyhow you have a large separation of scales between the thickness and your largest scale in the system, such that the dynamics of the two fluids is not really dependent on the thickness of the interface, then you are on business. Because even if the real interface is a few, the interface that you are simulating is a few millimeters, if the thickness does not change anything in your dynamics, then I mean you are on business, because you can think as if it is of a few nanometers. So this is the whole business. So the business is to move from the, if you want to attack it numerically in a way that is not a nightmare, is to abandon the idea that the interface is a singularity, to add in your free energy description. I mean, you may follow many different approaches, but I mean, let us follow the simplest. To add in your free energy description also a price that you pay because of the gradients in the density, and this is going to be, of course, proportional to the surface tension in your system. And then you write down the Navier-Stokes equations where you have an extra stress, and this extra stress, that in the literature is called the Korteweg stress, this extra stress is due to the fact that you have some gradients, some finite gradients across your interface. So the idea is, let me repeat it. Let's take a diffuse, this kind of models goes under the name of diffuse interface methods. So let's take a diffuse interface model where we have a given interface width. Let's develop an algorithm to simulate it. So to simulate the Navier-Stokes equations plus this extra stress induced by the width of the interface. And then let's check if the macroscopic mesoscopic physics is robust against this parameter, which is proportional to the thickness of the interface. Then you are on business, because you can change it and you still do not see a big difference in your outcomes. Otherwise, if it is not robust, so if the thickness of the interface plays a role, then it means that you are describing nanoscopic physics. But, I mean, you cannot claim that what you are describing is something which is macroscopic. So the idea of this lattice Boltzmann is to use Boltzmann equations, as you guess. And what is the idea here? I think one has to be very careful to not oversell, because there are many ways to oversell lattice Boltzmann that I do not like at all. So the idea is the following. The conceptual idea is the following. You have your Navier-Stokes that describes the continuum evolution of your fluid. And then you have, if you want, on the other extreme, the molecular physics. Right? You would like eventually to describe your continuum as a superposition of molecules. Right? And then you have to write the Newton equations, and you have to apply this kind of tricks or numerical methods that are based on molecular dynamics modeling. What is the drawback of this method? The drawback of this method is that because you are dealing with molecules, the time scales and the spatial scales that you are able to resolve are very small. Typically, meaning molecular dynamics is very difficult to go beyond the 1 picosecond or 10 picoseconds, 100 picoseconds if you use a very big supercomputer. And therefore, you understand that if you want to describe the evolution of a fluid on a macroscopic scale, within 100 picoseconds, nothing happens. The advantage is, on the other hand, is you really control the molecular properties of the fluid. The advantage of this method is that you have an Navier-Stokes equation that you believe they are correct on a macroscopic scale. And the disadvantage is that these, I mean, the parameters that enters here, I mean, you have to plug them. And especially when you have, as I showed you before, multi-components of multi-phase, you might have a problem in solving this equation in a simple way. The idea of the Boltzmann is to put in between. I mean, to not follow each single molecule, but to define a probability f to have a given molecule in a given position with a given velocity. So you describe the system on a kinetic level, and you write down the equations. I will be more clear in a few seconds. You write the equation keeping a memory of the fact that you have molecules, but you do not follow each molecule.
You describe only the probability to have a given distribution in a given position. And the other advantage of the method is that there are there is a very systematic way to let the continuum description emerge from the kinetic one. I mean, you can expand the system in a long wavelength expansions, and I will say a few words later on, and be able to recover the Navier-Stokes equations from this kinetic description. But the real advantage of the method from a numerical point of view is that, as I will show you in a few slides, the numerical method that is able to implement the Boltzmann equation, which goes under the name of Lattice Boltzmann equation, is fully local in space. So you might, we are going to be able to describe the evolution of this algorithm, and in the evolution of this algorithm, only what happens in the first neighbor's belt or in the second neighbor's belt, in the worst case, is important. What it means that from a numerical point of view, this is a real big gain, because first of all, you can import this kind of algorithms on massively parallel supercomputers in a way that is very simple to show, always scalable, which means that if you use 10,000 cores or 100,000 cores, you gain a factor 10 for free and for sure. And the second reason why this method is very powerful from a numerical point of view, is that being so local, it is also very simple to deal with complex boundary conditions. I mean, if you have a kink or a step, you need to solve and to adjust your boundary condition only locally, and for the evolution of the fluid, of the whole fluid, you don't need that. If you are on the other side of your domain, you don't need to know too much about what happens close to the step. While, I mean, in Navier-Stokes equation, as you know, the pressure being strongly non-local, if you want to solve the Poisson equation on a domain which is not simple, is a nightmare, and it's indeed a real bottleneck from a numerical point of view. So in a lattice Boltzmann and in Boltzmann equation, you pay the price that you downscale the description because you need to stay at a kinetic level. So you do not solve directly for these equations, but you gain the price that you have an algorithm which is fully local. And out of that, you can extract the continuum description via suitable long wavelength expansion. So this, I think, I can skip. So let me say one thing more. So let me be very clear. What we are going to do in the following is to use this approach to have and to set up a clever way to solve for this equation. I'm not going to claim that within my lattice Boltzmann approach I have more physical contents than what you have inside the Navier-Stokes equations. I'm not going to claim that I'm really controlling non-hydrodynamical, let me call it this way, non-hydrodynamical properties. There is a way to push lattice Boltzmann beyond hydrodynamics, much less under control. I'm not an expert, by the way, and therefore, I mean, if you want, I will comment later, but I mean, I will not say any real quantitative statement about that. So my goal is just to set up a clever algorithm, a black box, if you want, such that I can use it to solve for Navier-Stokes equation. It's very complicated, either geometries or with interface that goes around in your domain. And the other thing that is important to realize is that using this diffusive interface approach, you don't need to track the interface. I mean, the interface will emerge as a repulsion between molecules described by this equation. So there is no anymore any problem to need to solve a complex system with complex boundary conditions that are movable, because the boundary conditions, the interface is movable, but it emerges naturally out of the evolution of this distribution function f. Another problem which could be, which is very interesting, that I will say a few words, that has already been touched by Len, is that moreover, we know that there are situations, I mean, even if it might seem bizarre, there are situations where the hydrodynamical evolution must break down at some point, at some scales. For instance, Len told us a few days ago that if you are close to the contact line, very close to the contact line, if you adopt a pure hydrodynamical description, there you have a problem. Navier-Stokes are not well posed because you have a singularity. There must be something that goes beyond Navier-Stokes that gives you some effective boundary condition when you look at it from abroad, from large scales, but that if you go really in details, if you are able to go with a microscope and to see what happens at an nanoscopic level close to the contact line, some effects which are non-hydrodynamical induced by the fact that molecules must have a highly non-trivial physical behavior close to the contact line of the liquid and not the gas must emerge. And therefore, you know that even if you want to be at the hydrodynamical level, you must at some point go across all these scales, because at some point, at least close to the contact line, all these scales must be coupled in one way or another. And therefore, having a method which, if I expand it on the long wavelengths, gives me the Navier-Stokes, but that is still coupled in some sense to a molecular description because deals with the probability to find molecules, it might be again very powerful to attack with only one method the whole range of scales from molecular to macroscopic. And I will try to convince you that indeed this is the case. So, wow. Because this is a school, I mean, it's better to say a few things, but I mean, I think in the clearest possible way. So, maybe I will not go through all the details, but I mean, let me give you the idea of what is this lattice Boltzmann. Let me remove lattice and speak about Boltzmann. What is Boltzmann equation? Is an equation that gives you the probability, sorry, there should be a time, it's a time derivative, the probability to find a molecule with a given position x with a given velocity u. Sorry, with a given velocity xi. And the idea of Boltzmann is to say, okay, this probability evolves such that you tend to be close to the equilibrium, right? And the equilibrium is a Maxwellian. And the Maxwellian is determined in terms of hydrodynamical large-scale quantities. So the idea is that Boltzmann equation tells you how far you are locally from your hydrodynamics, in some sense. If nothing happens, the fluid is quiescent, temperature is the same, density is the same, you are at equilibrium, and the probability is just given by a Maxwellian with a mean velocity that is the hydrodynamical velocity, mean temperature which is the temperature, and the mean density which is the density. And then the Boltzmann equation tells you how much, if you are out of equilibrium, you have a change of density, change of temperature, how much this probability evolves, in which way this probability evolves in times, and you write down the equation in a way that you always tend to be close to this Maxwellian. In some sense, the Boltzmann equation is the law that you follow to restore local equilibrium when you don't have it in space. And the density, the usual density is the mean of the probability. The hydrodynamical velocity is the mean of the probability times the velocity of the molecules. The temperature is the mean of the probability times the kinetic equations. Very good. Then what you do, you write the Boltzmann equations. You make a very simple technical step, which is not important. So I don't want to. It's absolutely. It could be useless. It is useless indeed, but I mean it's easy for the implementation. You write the tendency toward the equilibrium in a linear way. The distribution function is closed. You see that this is just a transport, but then you have a relaxation toward this equilibrium that I call F0. And this F0 is the Maxwellian that I showed you before. So So you see, these equations is just a linear relaxation toward the equilibrium. Of course, it's only apparently linear, because inside the equilibrium, you have the density field, which is the mean of f, the u, which is the mean of f times psi, the t, which is the mean of f times psi squared. So it's a strongly nonlinear equation, but the way you relax is linear in this sense. It's just the actual value of the probability minus what you would like to be at equilibrium. So you write this equation, and then you can write an exact evolution for the hydrodynamical fields, for the average. You just average this first moment, second moment, and you write down these equations. The conservation of mass, conservation of momentum, conservation of energy. The problem, these are exact. The problem is that are non-closed, because in the evolution of the conservation of mass is closed, but the evolution of the momentum, you have the stress tensor. The stress tensor Pij is, you see, it is not closed in terms of the hydrodynamical fields, because you have again the whole distribution function of the tensors, and the same for the internal energy. So these are exact, but they are useless because they are not closed. So I should write also the equation, the evolution for P, the evolution for the flux of heat, and so on and so forth, and I would have an infinite hierarchy. So how people deals with that? Deals with that by doing two steps. First step, you say, okay, they are not closed, but I don't mind. I don't mind because I wanted to study the long wavelength expansion, so I want to be close to the equilibrium. So I may try to expand these unclosed functions in terms of how far I am from equilibrium. And this is the celebrated Chapman-Engskog expansion. And you say, okay, you see that here there is a small parameter, tau, which is the typical time of molecular collisions, which is typically very small, I mean, for any system of the order of picoseconds. So you say, okay, suppose I send the tau to 0, it's very small, so f is obliged to be very close to f naught, to the equilibrium. And therefore I expand. I say, okay, my f is my f naught plus tau, I mean, this is the Knudsen number, which is proportional to tau, plus tau first correction, plus tau squared as second correction, and so on and so forth. And also the time scales and the spatial scales you want to expand, because you want to control only the physics that emerges where the time scales and the length scales are much larger than these very small parameters. So you plug these multiple scale expansions inside this expression, and now because it's you put the small parameters in different orders, you are able to solve and to close the equations around the equilibrium. And what you find, okay, now this is the first step. And the first step is that if you do that, you find the Navier-Stokes equation on the continuum. This is good, so very well known. Then the second step is that if you want to solve it numerically, again, you are in trouble, because it's true that now the system is local, but you see that you paid a very high price because you had to move to a kinetic level. So these distribution functions depends not only on the position, but also on the velocities. Right? So you need to evolve a PDE in a 6-dimensional space, which is, I mean, it's a nightmare. It's impossible, but for all practical purposes. So the real gain, the real step forward, if you want, considering the numerics, is that there is another step that you can perform, which is again exact, and that allows you to use the tool numerically. The second step is that, by miracle, if you want, but it's not a miracle, you can reduce the number of molecular speeds that you need to describe the evolution of your probability distribution function from living on a continuum to live on a finite set. So you need only a finite number of speeds, of molecular speeds, to reproduce the Navier-Stokes equations in the long wavelength limits. So again, now you have a 3-dimensional space that you need to solve, and then you don't have any more 3 dimensions for the velocity phase space, but you just need a finite sets which might be 19, 27, depends on the symmetry. Now, this is a technical point which is not important. So you only need a finite number, 9, 10, and 19 speeds to reproduce the Navier-Stokes equations in the long wavelength limits. And this is, by the way, exact. I mean, it's not an approximation. You can prove it. And which is, I mean, it's very good for the method. I mean, from that point of view, the method is really on a stable feet. So to summarize, at the end, what you have to evolve a finite number of distribution functions, each one for each velocity, that is a finite subset, on a three-dimensional grid space. And therefore, you finally end with what people call the lattice Boltzmann equation, because you need to evolve on the real space the probability motion function on a lattice that could be cubic, hexagonal, and it depends on your tastes. You discretize time, of course, and the big gain, as let me repeat again, is that you need only a finite number of speeds, and therefore the problem becomes endable from a numerical point of view. You put all these ingredients, and in the long wavelength expansions of this discretized Boltzmann equation, you can prove that if the physics is simple, if the system is an ideal gas, you can prove that you recover the Navier-Stokes equations. So you have now this algorithm, which is fully local in space, is fully local in time, that if you define your density, velocity, and temperature as the average of this probability distribution function locally, it reproduces the Navier-Stokes equations on your lattice. Now the difficulty. The difficulty is we want an interface, right? Okay, the interface now it's a problem. Why it's a problem? Because I mean whenever you have an interface, we are far from being on a long wavelength limit, right? Because the interface is a sharp. You have strong derivatives, right? And therefore you must pay something. And the idea is, okay, let's keep our lattice Boltzmann equation as we define, and let's add forcing, a body forcing in my system, which should reproduce the idea that if you have an interface, I mean, two species want to repel each other, or if you have a gas and a liquid, you need to have a non-ideal pressure tensor, things like that. And therefore, what you do is you add a force which depends on the density in the point x plus times the density in the point x plus delta x, I mean in the nearest neighbor. So you again want something which is fully local. And it is simple, I mean not so simple, but it's possible to show that if you then perform the long wavelength limit expansion of the system plus this internal force, you end up, and depending on the shape of this potential, this interaction potential that you put between density in two different points, you end up with this forcing can be written as the gradient of an internal pressure tensor, and the pressure tensor has exactly the same shape that you would like to have if you wanted to mimic the Korteweg stress tensor. So by introducing these simple pseudo-potential interactions between density in one grid point and another grid point, you are able to introduce some non-ideal properties in your long wavelength limit. And now you see that the interface is completely, it's going to emerge. Not in the sense that depending on the interactions, you might have that and depending on this prefactor, which tells you how much the molecules interact, you might have that the two fluids, the mix, or you may have that the two fluids are miscible. Just to give you an idea, then you can expand this method to introduce also suitable boundary conditions to mimic any wetting properties at the wall in a under control way, in the sense that if you want a liquid and a gas with a given contact angle, you ask me and I tell you exactly which boundary condition you have to put to have that given contact angle at that given point. And let me just, for those of you that are aware about molecular dynamics, that at the very end the philosophy is not too different. I mean, in molecular dynamics it's true that people say, I also say, that is somehow more fundamental, because you deal with molecules and you describe the interactions between molecules with van der Waals or things like that. But nevertheless, you have to plug the parameters in your potential, right, to end up with something that gives you the mixing properties. And in our approach, we don't have molecules, we have a continuum, because we have a probability distribution function of molecules, and we have, again, the three parameters that are the shape of the potential and the interactions. So the philosophy is very similar. The advantage is that here we are close to the hydrodynamical scales. So we are not limited in time by describing each single collisions between each single molecules, as the people that need that works in molecular dynamics have to do. Just to give you the idea of a few applications, a very, I mean, now a little bit outdated, but a few years ago was very warm field, is the problem of what I call the conspiracy between roughness and hydrophobicity. What you imagine, if you have a surface which is rough, in principle you would imagine that the friction should increase because it's rough. But on the other hand, it is also true that if the surface is hydrophobic, you tend to trap gas bubbles close to the surface, and because there are gas bubbles, the liquid may slip very well because it does not touch the surface anymore, and you have a free shear condition here. So it is very well known indeed that if you can even build up surfaces that have a patterning on a nanoscale, like the one that I showed you here. These are a few microns, the distance, and you coat the surface with the hydrophobic material, and then you have that water droplets are completely repelled from the surface. They tend to form. If you put a water droplet on the surface, instead of spreading, it just stays like on the top of a lotus leaf. So this is the typical situation that you would like to use to benchmark your model, right? Because now you see, I have a complex surface, I have a complex physics because I have gas and liquid, and I have hydrodynamical scales because I want to study the slippage. And you can do it in two different ways, but let me skip this. And we did it a few years ago, and we are very satisfied to see that we were really able to capture a quantitative agreement with molecular dynamics. What I mean for quantitative agreement, I mean something like that. For instance, we set up these lattice Boltzmann models. We put all the obstacles on our surface. We call, as I told you, that one can decide the contact angle. So we choose a contact angle very high, close to 180 degrees, and we let the liquid to spread over this surface, and you change, depending on the pressure, the total pressure in the system, you may go from a situation where you invade the groove, or to a situation where the air is trapped, the vapor is trapped close to the hydrophobic surface, and therefore the liquid can slip without seeing the roughness. And we were able to put on a quantitative level on top of one of the other the lattice Boltzmann simulation with the molecular dynamics concerning the static case. Static case, it means really the thermodynamics. I mean, that's how much the pressure versus mean density inside this system. But then the advantage is that with lattice Boltzmann you can shear. I mean, you might have hydrodynamical evolution because you're not limited anymore on time scales, and you may start to study. Okay, this is we skip. You can start to study a whole series of questions that are really connected to the evolution on long wavelengths, and you may study the velocity profile. So you may study a lot of things that I don't have time now to enter into details. But the message is the philosophy you see is trying to match the method with something that you believe is more accurate on a range of parameters. Once you have it, then you can push the method also in those regions in your phase space where the other methods cannot say anything. Let me then attack another problem, because this problem was interesting, but it was in some sense without contact line, right? I mean, I just want to study the flux of liquid over a rough surface. Let me now tell a few words about the issue of the contact line. This is a very interesting issue, and because, as Len told us, hydrodynamics here fails. And in order to deal with hydrodynamics, you need to introduce a slip length. I mean, you need to allow the contact line to move. You need to relax the idea that the velocity is at zero at the wall. And this slip length in the hydrodynamical description comes out of the blue. I mean, you just have to assume. I mean, there is a slip length. In any diffusive interface description, on the other hand, because the interface now is not a line, but it has a thickness, this slip length naturally emerges because you may have, for instance, mass flux across your interface first. And therefore what happens is that you have a method where not only you have the interface which emerges naturally, but also where you don't have to assume anything about what happens close to the wall. In some sense, the interface already does the right job. I mean, it is thick, and it relaxes the divergence of the hydrodynamical level. Indeed, as a matter of fact, even though I'm not able to prove it, the slip length that you measure when you have this finite interface thickness is always of the order of the thickness of the interface, as you can imagine. So not only the system is good because it allows you to follow the interface, but it is also in some sense self-consistent in the sense that it gives you a way to relax the hydrodynamical divergence. It might not be the right way, I don't want words, but certainly it's a way. And we played a lot of, just to give you again how quantitative one can be. What we did is, for instance, let me just give you just the idea. What we did is, let's try to study this contact line problem in the simplest situation that you want to try to control. Let's have a liquid, one here, two on the other side, and let's coat the walls such that you have a contact angle theta and a contact angle 180 minus theta on top, such that if you don't do anything, you have a straight interface. I mean, it's trivial. And then let's shear. We move the top wall on one direction, the bottom wall on the other direction. Because you shear, the interface starts to bend, and if you shear more and more, it breaks. It breaks down. Because you started to entrain the liquid, and therefore you remove the liquid from one side, and you have the plate here, which is coated by droplets or by the thin film of one liquid, and vice versa on the bottom plate. That's why when you jump out suddenly out of your shower, you have droplets that stays on top of you, right? Because I mean you entrain liquid on your skin. And this is a nice problem because you can solve it exactly in lubrication approximation. So you have it's a problem where you can control the hydrodynamical description in an exact way. And then you want to put on top your mesoscopic approach with lattice Boltzmann and see how close you are. And let's, I will not spend too many words about how you solve in lubrication. You can solve it exactly, believe me. There are many free parameters because there is the wettability properties, the viscous ratios between the two liquids, the capillary number, of course, and the other parameter, which is key, is what people call the Kahn number. That is the ratio between the thickness of the interface and the scale of your system. In our case, the thickness of the interface is also of the order of the slip length. And if you play this game, so you solve. Okay, I'm sorry. Let me say one word more about the method, because up to now I told you about liquid and vapor. Now we have a different problem, right? Because I told you that this is I don't know, oil and this is water. So these are two components. And but I guess you may imagine very easily that you can easily extend this approach. I mean, this lattice Boltzmann equation, this lattice Boltzmann, to multi-component systems. You just need to introduce different probability distribution function for different components. So you're going to have a probability distribution function for water, probability distribution function for oil. You're going to have a lattice Boltzmann equation for one, water, let's say sigma 1, another for oil, sigma 2, or sigma A and sigma B. And then out of the long wavelength expansion, you extract the evolution for the total density, the sum of the two, the evolution for the total velocity, the sum of the two velocity, and so on and so forth. And if you have an interaction between the species, so between the probability distribution function, you might have a situation where you demix. There are a few technical steps, but very simple. I hope you believe me. So you are also able not only to describe a liquid vapor, but also many components. And putting interactions between the distribution probability of different components, if the interaction is repulsive, the two components mix. If the interaction is attractive, you have two miscible fluids. So you build up this lattice Boltzmann, and I show you here just to give you a flavor of how quantitative you can be. You may really, I suppose here, for instance, let us look just at this plot. I suppose here, I studied this problem, right? I mean, the problem of two fluids under shear, right? And I plot here, for instance, the angle that I measure in the middle of my cell as a function of coupling, so as a function of how much I shear. And here, for instance, I show you a typical bifurcation diagram where you see these are the symbols are the results from the lattice Boltzmann for different slip lengths, and the continuous line are the results from the exact lubrication theory with a slip length that is the one that I measure in the lattice Boltzmann. Because I remind you, lubrication, Bain Navier-Stokes, need a slip length, otherwise you cannot solve. And the agreement is perfect, and you see that you have a typical transition. Yeah, there is a critical capillary beyond which you don't find any solution anymore because the system breaks down. So you don't have anymore a stationary profile. And by the way, you see there is also an instability that you have. The lubrication gives you two solutions. For a given capillary, gives you two possible angles in the middle of your volume, while the of course one of the two is unstable, and so the numerics gives you only one. I mean, you will never be able to get the other branch by using a numerical middle being unstable. Okay, here there was a movie, but I mean I don't have my laptop, so you will not see the movie. Just wanted to show the movie of this interface that is sheared, and then you at some point you break it, and so on and so forth. Let's go on. And let me maybe just a short advertisement you can do much more. And for instance, you can study the same system under gravity. And therefore, this is really the so-called Landau-Levy problem. It is the coating of a plate. Right? It is you have a bath, you have a plate with some wettability properties, and either you pull or you withdraw the plate, and you want to study what is the thickness of the film that you deposit on the plate as a function of the capillary number, as a function of how fast you pull or you withdraw. These are very important technical problems, as you can imagine, because many times you want to remove as fast as you want to improve the productivity, but if you remove too fast, there are instabilities, the films break down or droplets everywhere. So it's, from a point of view of, there are many applications that are extremely important that are connected to these very simple experiments. Right? And in the last few years, we also had a lot of very interesting experiments about that. And the typical question, there are two typical questions. The first question is, what is the critical velocity that I have to trespass before the film is deposited? Because if you remove very, very slowly, the contact line slips, and therefore, you remove the plate which is dry. You do not deposit the water. If you exit from your bath very slowly, you should be able to exit dry. Okay? But if you remove very fast, then you deposit the film, because you entrain the water. And so the typical question that people want to control is what is the critical velocity that you have to reach before the entrainment is reached, and then what is the thickness of the film, because also the thickness of the film depends on the velocity. And this is again, and the opposite problem is even more interesting, that is when you push. Because when you push, is air that must enter in water, which is even much more difficult, right? Because it's less dense, viscous. And it is another problem where lubrication, if you apply it in a straightforward way, is in troubles. Why? Because you see that if you have to entrain air into the liquid, this is the liquid, this is air, the angle of the most important, from a dynamical point of view, component, the liquid, is very high. You are certainly not in a situation where you can apply the thin film approximation, right? Because here the film is extremely big. It's not a small angle. And therefore, but nevertheless, you can use lubrication. It's Jakobs Neuger a couple of years ago, 3 or 4 years ago, was able to generalize the lubrication approximation also to very high angles, if you want, because the control parameter there is not anymore the angle, but it's the derivative of the angle. So you might have an angle which is high, but if it is the same constant, you still may apply lubrication. It's a very nice paper, by the way, Physics of Fluids, 2006. And therefore, we also, for this problem, again, we try to match the lattice Boltzmann with lubrication, with the generalized lubrication, to be sure that the method is validated, if you want, and then pushing the system into a situation where lubrication does not work anymore. And then we skip details. And in the last few minutes, I'll tell you something. Well, here there was another nice movie that I'll tell you something about 2 or 3 applications, just to capture the attention. Another very recent application of these methods is within the realm of glassy systems. In which sense? In the sense that now you can really, in some sense, close your eyes and being optimist and pushing the system to a situation where you don't have one interface or 2 bubbles, but you have only interfaces, like an emulsion or a foam. And therefore, where you have the two components and you decrease the surface tension to such a tiny level that you might have a situation like this, which is stable forever. The droplets tend to not coalesce because the surface tension is almost at zero. Or a foam, like here, where the volume fraction of one species is almost at zero, and you have only one liquid which is separated, which is made of droplets separated by the other droplets by a very thin layer of gas. And this method has been used to, there are not so many other numerical methods that are able to attack a problem like that. Because here, you have really a lot of interfaces, you have a multi-component, and you want to shear. It's really a complex physical problem. And people have used it to study Newtonian rheologies, field stress, things like that. It's very, very recent, so it's very little is known. But at least from the point of view of feasibility, these are nice proofs of concepts. Then in the last few minutes, let me also say another word about the application to high Reynolds numbers. Up to now, we only spoke about capillary numbers, Stokes flows, moving contact lines, but in a regime where the dynamics was completely predictable. The method has, on the other hand, been also widely used. Indeed, it has been developed originally 30 years ago to study turbulent flows. It is to study, to have a good, at this time people were hoping to have let's say, method that we use to attack turbulent flows in complex geometries. And they indeed even had some success. There are now commercial companies, big commercial companies, that sell computational fluid dynamics expertise based on the Lattice Boltzmann methods for turbulent flows. BMWs are typically, the BMW profile is typically optimized thanks to numerical simulation made by using Lattice Boltzmann, for instance. But I want to give you the hint on how difficult it is to use it in this regime. And I want to do it by making this very simple order of magnitude calculation. What is a turbulent flow? A turbulent flow, I don't know how much you know, but a turbulent flow is a flow that you steer it at large scale, you produce big vortices, and because viscosity is very small, or you steer it very intensively, you also produce the energy that you put at very large scales by your steering is not absorbed at those scales, but tends to be transferred to small scales. You produce small vortices, small hurricanes, and you have also activity, highly non-trivial and chaotic activity that you see with your eyes at scales eta that are 1/1000, sometimes the scale of your steering. So it's a flow that is chaotic on a wide range of scales. And why it's difficult to deal numerically, because you need to resolve a lot of scales, of course. And why it is very difficult to deal numerically when you have interface, because not only you need to resolve all these scales, but you also need to resolve the interface. You have another width in your system, another length scale in your system that you must be very careful about. And typically, if you make this order of magnitude, what you have? You have your grid unit, 1. Then you have the thickness of your interface that I told you could be 3, 4, 5 grid points. Let's say 5 to be conservative. Then you want the viscous scale, the smallest scale that you have in your turbulence, which must be larger than the width of the interface. Why? Because the width of the interface in reality is 1 nanometer. So it would be unrealistic to imagine to have a turbulent flow with fluctuations that are up to 1 nanometer. Do not exist. So you want that the smallest turbulent fluctuation is nevertheless larger than the width of your interface. So the smallest turbulent fluctuations must be here. Let's say a factor 2. Then you have this range of scales that I told you between where you force and where you dissipate. In a turbulent flow, I told you 1000. Let us be optimistic and say that it is at least 100. That are all scales where you have a chaotic evolutions, and that from where you force to where you dissipate, there are at least 2 decades. Now you multiply 5 times 2 times 100. Let's say a factor 2 for the box. You easily reach 1000. So you really reach that if you want to simulate a turbulent flow with an interface, at the very least you need for each dimensions 1000 grid points. That in 3 dimensions, which it means 1000 cube, let's say 2000 if you want to be on the safe side. An omega simulation 2000 cube is almost a state of the art on the biggest computer that you have in the world. I mean, you can do 4000 maybe, but you cannot do 20,000. Nobody. Therefore, you see that whenever, and this is really, let's say, the minimum requirements that you would like to satisfy to attack in a quantitative way a turbulent flow, so high Reynolds, with an interface. Therefore, I mean, the minimum that you may, the maximum that you can do is the minimum that you would like to have. So one crucial question would be, for instance, to simulate how you cook your pasta. I mean, that's where what I was mentioning at the beginning. This is numerically speaking, it's tough code. I mean, that's to have convection. So you heat from below, you cool on the top, and you have liquid and vapor, and you want to follow the nucleation of bubbles, and you want to understand how much bubbles change the property that you the way you transfer it from the bottom to the top. This is important not only for cooking pasta, but also for instance cooling inside the nuclear power plants. And very little is known. And very little is known experimentally, very difficult to do numerically. And I mean, Lattice Boltzmann is somehow promising. I'm not saying that we will ever reach a very quantitative results, but I mean, I would say that it is at least promising. Here there is the problem of the latent heat, but I will not enter into details. I mean, the good news is that you can really control a latent heat. So you may set up a Boltzmann description where, because I mean, of course, if you want to be quantitative, here you need to take into account of the heat that you need to spend to nucleate the bubble, right? And therefore, if you really want to be quantitative, your middle, the numerical middle, must be able to follow the thermodynamics in a realistic way. And the good news is that indeed we know how to do it. I mean, using this Boltzmann approach. Then let me. Okay, there was another nice movie. Yeah, maybe let me say, just because it's a school, let me give you another seed of information. The frontier, the technical frontier of Lattice Boltzmann concerning non-isothermal flows is in the difficulty to describe in a consistent and under control way also the evolution of temperature. Because temperature is a second order moment, it's the kinetic energy. And in order to do that, if you want to do it really from a first principle, I mean, as a Boltzmann would have done it, and you want to do it in a numerical way, you need to have a finite number of speeds. And unfortunately, the number of speeds grows enormously, which is not that bad. I mean, at the very end, we don't pay about our computer time. I mean, we pay, but not in real money, right? So, I mean, if the code takes twice, okay, it takes twice. I wait 2 weeks more, right? The bad news is that not only you need to have more speeds, but these speeds also connects, you see, not only first neighbors, but also second neighbors, third neighbors. And this is a problem because the system becomes more and more non-local, and the behavior close to the interface becomes less under control, and especially the behavior close to the boundary condition is much more difficult to handle. Because now the boundary, suppose you have a boundary, a wall here, not only this speed will collide, but also the one that is here, also the one that is 3 neighbors away. So the control of the boundary condition becomes feasible if the boundary condition is simple, very difficult, sometimes out of control if the boundary condition is not simple. So temperature, a real self-consistent evolution of temperature by using lattice Boltzmann is still, I would say, really at the frontier. I mean, people have their recipes, but I mean, different groups have their different recipes. This was another example of a turbulent flow, the Rayleigh-Taylor instability. Again, where you have a cold fluid on the top and hot fluid on the bottom, and you want to let them to mix because of gravitational instability. And this is something that becomes, it's very interesting from a turbulent point of view because it's becoming more and more turbulent. More you wait, and more intense the fluctuations become. So it's, I mean, from the community of turbulent theory is a good problem in some sense. Okay, this was a movie. This is a joke. Let me conclude. Because I mean, I want to advertise. I mean, we have we are actually working in Rome. We have a lot of postdoc positions opening now, and we have 2 big grants from the European Union, fortunately. One concerning if there were movies. I mean, because advertisement was supposed to have the movies, but I mean, there are 2 big European grants now in our group. One is concerning microfluidic, so evolution of droplets or bubbles in complex geometries, mainly using lattice Boltzmann. Another is concerning turbulent flows, not necessarily using lattice Boltzmann, sometimes yes, sometimes not. And so we are hiring, if you are, the salaries are good, around 2,500 euros. And so if you are interested, please contact us. And I think more or less this is, I think I can stop here. I couldn't refrain from, my phone is all the time sending me this message, keep calm, and then I said, okay, I will use it.
Okay, any questions?
Yes, about the diffuse interface. I guess that you can somehow control it, meaning make it sharper and sharper.
Yeah.
I guess by varying the force in the Boltzmann equation.
Yeah.
And how robust is that? I mean, there's.
Okay. It is easier to make it larger and larger.
Okay.
So but which is not trivial. I mean, in the sense that it's a good test, because if you make it larger, you have more grid points inside your interface, so your gradients are smaller, and therefore you are closer to the equilibrium, and therefore your lattice Boltzmann should be closer to the continuum. And on the other hand, playing the game with making it sharper and sharper, it's a big art. It's a big art.
Yes, because
you need to fine-tune the parameters, to fine-tune the interaction potential. And to fine-tune the geometry. I mean, sometimes what works well in one geometry does not work well in another one. And I mean, let me say, people is not really interested to make it sharper. The people are interested to make the density jump larger, which is in some sense the same. I mean, because you want to be close to, I don't know, I mean, for instance, a liquid vapor density jump of 1,000, right? If you have, I mean, I told you, it's a big art. And if you want to reach, for instance, a density jump 1,000, you really need to fine-tune the parameter, the models, putting counter terms, adding a small correction here and there. So it becomes really, I mean, a numerical art.
But theoretically, from the Boltzmann to the hydrodynamics?
Theoretically, you know, theoretically, the point is that you never know how close you are. Put aside the stability of your code. You never know how far or how close you are to the equilibrium when you have big gradients. Right? So it's, I mean, you know that close to the interface, you don't know what you are solving. But then one can say, I don't mind, because I don't mind the interface. And then the problem is about the stability of the code.
It's a good method with some good applications, and your good presentation made it sound a little better than it is. It's not quite as good, the method, as you said.
Happy.
So there are two things. One is you're carrying around 19 variables to represent 3,
Yeah.
which is a minor cost. The other thing is it's local, sure, but it's slightly compressible.
Good.
So the number of time steps you have to take to propagate the sound wave across the system and back is exactly the same cost as solving the POSOG problem in a not incompressible system. And we have advanced ways of doing POSOG.
Thank you for the remark, because it's very it's correct. I mean, I forgot to say. I'm sure that I added in some slide that the method is, because it's local, it's compressible. You always have a small compressibility. I mean, Mach number is not 0, and therefore you have sound waves, and therefore you must be careful about those effects. About the efficiency compared with solving Poisson equations, I have to say, frankly, I don't know, and second, in some sense, I don't mind. I repeat, because I don't.
So it's the cost of how many time steps
Yeah.
to propagate a sound wave across the system and back.
Yeah, this is the.
Cost. It's number of iterations to sweep.
I perfectly agree. And indeed, I mean, what I wanted to be clear, I mean, I really say that at some point I will try to oversell, in the sense that I always spoke about the good aspects, right? But I wanted to send the message that for some situation where the physics is very complex, interface, wetting properties and things like that, it might be, I don't want to say the method of choice, but one of the possible methods of choice. On the other hand, I would never use it to study turbulent flows, isotropic, isothermal, without boundaries. I mean, it would be completely crazy. There are much better methods that attacks Navier-Stokes equation to court, and that are infinitely more accurate. Because another point that I didn't say, but I think I had a remark, you also pay the price about the accuracy. The method is, at the very best, if you work hard, the second order accurate, close to the boundaries. So it's, again, if the system is so complex that you must anyhow do something, I think it's good.
A quick question and comment. Actually, you had a slide, I forgot which slide was, about the contact line singularity and the thickness actually taking care of that. And you mentioned, you sort of blame that actually on the divergence term. But another way of looking at it, and we see that actually molecular dynamic simulation, is that you assume that your fluid is Newtonian everywhere.
Yeah.
Because immediately at that contact point, considering the shear stress is very high, so Newtonian fluid assumption breaks down and you have a non-Newtonian fluid.
Yeah.
And I can actually interpret that into types of results very differently.
Yeah, still, I I mean, if you start from your Navier-Stokes equation, you must give me a recipes to how to change the viscosity close to the contact line, such as to take into account of this non-Newtonianity, right? I mean, it's either you introduce a slip length or you introduce some new physics, I mean, like non-Newtonian effects. That I mean, I agree with you. That might play a role, but they are not inside your original Navier-Stokes equations. You have to postulate them in some sense. This was my only claim. I mean, that on the other hand, this is a method that, thanks to the thickness of the interface, it gives you for free. I say that maybe not the real one, maybe it's no Newtonian effect, but I mean, in any case, this is a method that, thanks to the thickness, gives you for free a sort of slip length. It would be very, I mean, I don't know if we will ever be close to that. It will be very interesting, you know, to have good experiments and to understand indeed what is the physics close to the contact line. I mean, what is the real mechanism that releases the singularity? Because I mean, after all, the droplet moves, right? So I mean, the singularity is released. People believe it's a thermal activation. So there are studies about fluctuating hydrodynamics, putting thermal fluctuations in the Navier-Stokes equation. Other people believe it's not it's non-Newtonian effects. I mean, there are different statements. To my knowledge, no experiments. I mean, there are now a few experiments about this thermal fluctuation stuff. But I mean,
One very quick one. At the end, when you're talking about the temperature effects, you said boundary conditions were difficult.
Yeah.
Is that implementation of known boundary conditions, or is that even knowing what the boundary conditions?
No, it's the if you wanted the implementation.
So
I mean, which is connected to that. You might, I mean, on a molecular scale, you might not know what is. I mean, people claim that the right boundary condition should be no slip. Also for temperature, you may have a slip temperature, right? So it's. I mean, the two goes together.
right, that was. A question from a complete ignoramus regarding this technique. Grid adaptation, is that an issue?
It is. Grid adaptation is an issue. I mean, you can implement it. Not easily, as all grid adaptation are never easy. People do it, especially those that works, you know, in specific commercial applications. I mean, where if you need to resolve the profile close to your BMW, you need to adapt your grid. To use non-structured grids or grid refinement, and all the let's say the tools that people have developed in other lattice methods can be applied as well.
Any more questions?
What about the inclusion of surfactants? Can this be done? They are confined to the interface?
Yeah, people also did it. You can do it in different ways. You can do it by introducing a new species that likes to sit on the interface. So you put a interaction potential with the other two species, such that I mean the energy is minimized when you are on the interface. Otherwise, people did it also in a much more, let's say, brute force way. Really putting, if you want, solid particles that have a thickness and that they move around your fluids, and that again they have interactions such that a sort of colloids, if you want. And you can do it. I mean, of course, you can't do it from first principle. I mean, you don't really have a kinetic description of that. You see, I mean. There you really invent a lattice Boltzmann description, such that in the continuum limit you have a sort of surfactant that goes around in your system. It's really a model.
You mentioned the slip length, and I guess that was between liquid and solid. What about the liquid and the other liquid in the example you showed, can you also say something, or do you see something like that?
Say it again because oops. Oh, I don't have the password. I'm not sure I understand the question. Sorry.
Oh, you had a comparison where you had a shearing and two liquids.
Yes.
And there you said that you had to tune the slip lengths.
Yeah.
Where I
You mean if you have a liquid and gas?
No, this was.
You're speaking about the shearing of the
Do you mean the lambda?
of the system like that?
Exactly.
Yeah.
And
Yeah, I show you the case where I have one liquid here and another liquid here.
And the lambda was a slip length between the solid and.
No, the lambda was the thickness of the interface. I mean, and as a matter of fact, the thickness of the interface reflects in an effective slip length. I don't put any slip length in my system.
Okay.
You see?
But you said you compared with thin films, and there you probably did something like that.
In film, but always in the lubrication with two liquids, and with a slip length in the lubrication approach. So I use in the lubrication approach the slip length that I have to put in the lubrication approach in my analytical lubrication solution. I choose it to compare with the numerics. I choose it equal to the width of the interface.
Yeah. So my question is the velocity across a liquid-liquid interface, is this continuous or does it also slip?
Well, you know, the liquid-liquid interface is thick, so everything is continuous. You see what I mean? That's you have always a few grid points around the real interface. Is like that. So you always have a few grid points, and you have the velocity inside. You have also velocity inside your interface that I don't know if you want to believe to, because I mean it's something that is from the aerodynamical point of view completely out of control.
So there is no jump.
There is no jump.
Okay.
Of course, like in any numerical methods, you have also a lot of garbage that you need to control. I mean, this is another point.
Also in the limit, there would be no jump. In the limit where the width goes to 0.
No, in the limit, when the width goes to 0, there is a jump.
Okay.
There is a jump. I mean, if I plot, suppose I plot the velocity across this direction, right? And I have here something like that, and here something like that, right? So I'm going to have something, I don't know if positive or negative, but I mean, I'm going to have, here there is the interface, I'm going to have something like this, with a few grid points. And if I would be able, but I'm not, to reduce, this is going to be more and more sharp.
And this you can control by tuning the interactions.
Yeah, but I mean, within many limitations.
Okay. Thank you.
Right, okay, so it's lunchtime, so thank Luca once more.